Hello everyone, my name is Guillaume Lobet and today we'd like to present you some of the work we've been doing in the lab on developing a virtual phenotyping pipeline for the evaluation of root hydraulic properties of maize plants. This work was primarily done by Adrien Heymans, but today I will present it. So the question we wanted to ask was whether maize landraces that have evolved from very different environments, so you can see here different environments in Mexico, for instance, with very high differences in either the temperature or the precipitations that create very different conditions for the maize to evolve. How does these landraces have evolved accordingly to these environmental conditions? What could be observed is that the landraces have a very distinct roots anatomical features and architectural features. So you can see here 8 different landraces that have either small or big root systems with different root growth rates, root densities and so on, but also associated anatomies. So you can see that the anatomies are also very different, with small roots or much thicker roots with different levels of parenchyma, number of vessels, and so on. And what we wanted to do was to assess whether we can link this diversity in anatomy and architecture with the different environments that these different lines evolved in. And to do that, we used a multi-scale modeling pipeline that we developed in the lab. Again, this is mainly the work of Adrien Heymans. And that pipeline combines organ scale models that allow us to estimate organ scale hydraulic properties, so radial and axial conductivities, for instance, for different types of anatomies. So we can take explicitly into account the anatomies measured for the different landraces. And we couple that with a root architectural models to represent the different architectures. So within the models, we explicitly put together different anatomies, different architectures, and we combine that to estimate root system scale hydraulic properties. Then what we can do is put these root system scale hydraulic properties in different environments, and then we can test all the different types of combinations. So we can take all the different landraces and put them back into either their own environments, but also in all the different environments that all the landraces came from. And I will present you some of the results, very briefly, some of them the major ones. First, one thing we could observe is the water uptake dynamics of the different lines. And what we did see was not really very strong adaptations of the different lines to the different environments, but more like the fact that the larger root systems with a more uptake capacity always take up the more water. That's for one thing. So they take up a lot of water if you have more roots. But on the other hand, if you look not at the total water uptake in itself, but the water uptake efficiency, so you take the total water uptake and you divide that by the amount of carbon that was invested in the root system, there we can see a shift in the best lines, and the lines that are the most efficient are usually the smaller ones. So if you take both the amount of water and the amount of carbon, then the smaller lines are more efficient. And so what we could quickly see is a trade-off between this efficiency and the total water uptake extraction. If you want to uptake a lot of water, you have to have a big root system, but that comes at a very high carbon cost, and in some cases that also can lead to dangerous situations for the plant. If you uptake all the water, there might not be any water left for the growth afterward. So very quickly here, what I wanted to show you, and again this is a very brief overview of this phenotyping pipeline that we have developed in the lab, is that we could identify a trade-off between the efficiency and the overall performance. So there is a trade-off for the plants there in terms of water uptake. We could see that the virtual phenotyping helped us analyze some of the G by E, so genotype environments interactions. But we have to keep in mind that the models can only inform us about one part of the reality. Here we only look at the water aspect, but there are many more. Thank you very much.